Okay, so the next team is team 46.
Alrighty, so good afternoon, everybody. I want to thank you for coming out here today to listen to our nice, lovely senior design project. My name is David Ospina.
My name is Abby.
My name is Ricky.
I'm Danny.
And I'm Alejandro. And we will be presenting the Maskless Photolithography device. Now, to start, I want to give you guys a brief overview, more like a top-down view of the chip creation process. And this will give you a better idea or the scope of our project. And to start, integrated circuits are the building blocks of modern electronic structures, and they provide functionality and processing power in a small and compact package. Put together, this chip or brain provides the devices with the everyday lives. Let's use the modern life. Alrighty, so how do we do this? This process is called microfabrication. This process allows us to construct miniaturized electronic structures, and it also involves a lot of different techniques that I'll be going over in the next slides. So here are the four main techniques that are used in microfabrication, where we have etching, implementation, deposition, and the one that we thought was the most important and efficient part of the process called photolithography. But what is photolithography? Photolithography is the art and science of transferring patterns onto a semiconductor material. And I want to show you a little video to show you a little bit of the process. Here we have the photoresist being applied, which is just a light-sensitive material that goes onto the wafer surface. After that, we'll go and expose, which just carves out the predefined design onto the wafer. And then after that, we go to etching and developing, where we just selectively remove all the material onto the actual silicone wafer. Now let's talk about the two different techniques that go into photolithography, with one of them being conventional/traditional photolithography. And this involves using a physical photomask with a predefined pattern. Advantages here is that there's already well-established technology, which just means that there's a proven track of functionality. Another advantage is that it actually has higher resolution, which means that it's a little bit more cost efficient and you can get a smaller feature size, which just means that you just put more chips onto the wafer. For maskless photolithography, there's no physical photomask that's involved, and you can create this pattern by using a computer-controlled laser or a software where you can just upload images. The advantages here is that there's also just a faster turnaround time, meaning that since there's no mask creation or mask maintenance, you can just iterate and prototype a lot quicker. Another advantage would just be that there is just greater pattern flexibility, which just means that you could create multiple images onto the wafer. So I just wanted to pass it on to Abby to talk about the drawbacks of photolithography.
So these are two examples of current machines. The picture in the center is the photolithography machine found in Beam's clean room up on the 8th floor. This machine costs millions of dollars, and it also is very time inefficient because you either have to make the mask yourself or outsource it, which will take days. There are some machines out there, such as the Microlite 3D, that does not require a mask, but this is still in the range of like $50,000. So for our student proposed project, we wanted to make a maskless photolithography machine that would be accessible to undergraduate students wanting to get into integrated circuit design. To do this, we came up with four main benchmarks. The first is that it should be economical, so less than $2,000. Second, it should be maskless, so that we could have a lot of flexibility in the types of patterns that we can create. Third, it should be user-friendly, not very coding intensive. And then finally, since we're doing microfabrication, it should be on the micro level, so it should be around 10 micrometers for each pattern. This is the final product that we came up with. There are three major sections. The first being the device communication and all of the electronics. This includes a Raspberry Pi and an EVM, which is our image projection system. The second is the optics, which starts in the EVM, and then the light is focused through a lens cell with a bunch of different lenses. Finally, we have our stage, which holds the wafer and can move in both the X and Y direction so that the entire wafer can be exposed.
To achieve our goal of having maskless features, we adopted a technology called optical projection lithography. Specifically, we were using the DLP 2000 evaluation module from Texas Instruments. In this evaluation module, there's a special chip called digital micromirror device. In this device, there's thousands and perhaps millions of micromirrors that can be controlled electronically and individually. This special and unique feature allows us to have essentially like a flexible mask instead of having just one hard mask. And at the end, we have a light source that is at designated wavelength that can expose the photoresist. This light is shown onto the DLP chip, and the micromirrors reflects off a generated pattern, so it's off through the projectile lens. This evaluation module is then incorporated into our optical engine shown here. Oh, sorry. The outer casing of the optical engine was specifically designed so that it can not only protect the internal components, but also fit right onto the microscope stand. We use the microscope stand to adjust the height of the optical engine to fine tune the focus plane, so we can expose the pattern on the wafer surface. Inside our optical engine, there are three major components. There's a PCB board that holds the evaluation module as well as the interconnects that connects to the Raspberry Pi, which is my microcontroller that controls the overall system. There's also a backplate. The PCB board is mounted onto the backplate. The backplate also ensures that the image coming out of the evaluation module is shown directly perpendicular to the wafer surface. And at the bottom of the backplate, there's also a circular rest plate for our converging lenses. And then lastly, we have an objective lens holder, which, as the name suggests, holds the objective lens. Altogether, an image is generated through the evaluation module, and before it diverges, we have two sets of converging lenses that collect the light and focus into the objective lens that has 10x magnification. In our case, we flip the lens so we can actually shrink the image in 10x magnification, and the generated pattern is exposed on the wafer surface. In terms of the overall mechanical design, there are four major components to the mechanical assembly: the stand, the optical engine, the wafer stage, and the XY stage. The XY stage was built so that we can move the wafer in small increments in both X and Y directions. The wafer stage itself is mounted onto the XY stage, and we have two purposes of building this XY stage. The first one is to step and repeat small patterns over the entire surface of the wafer. The second reason is that we could either break down a big image and then print a small portion of it and stitch them together. The working mechanisms of the XY stage is simply using stepper motors that is coupled with linear least screw assemblies.
So putting together all these aspects of our design into an overall signal flow diagram, we start with the Raspberry Pi, which, as you have mentioned, is the overall controller of our system. The user can interact with the Raspberry Pi with an external keyboard and mouse and see its display on the monitor. From here, the user inputs the exact image that they want to be printed onto the wafer. This Raspberry Pi then communicates with the projection system through I2C, which is just a serial bus communication. The output of that is the light that is then directed into the lens cell, which we show in the optical engine. That image is demagnified and then directed onto the wafer, which is coated in the photoresist, which is that light-sensitive material, so that way the image can be actually exposed onto the wafer surface itself. And then simultaneously, while all this is happening, we have the movement stage with the XY stage. That is also controlled from the Raspberry Pi end. We have a serial bus that also communicates using Arduino Uno that controls the stepper motor driver system. There are digital signals, from the Arduino Uno that control the stepping and the direction of the stepper motors. Those go into drivers, which then output current pulses that control the stepper motors. Those result in the direct amount of torque that is needed to move those red screws in the assembly to then move the XY linear stage. Then all of these together then result in the pattern exposed onto the wafer movement, and then another exposure, and then another pattern exposed on the wafer, so then you can stitch together multiple images onto the wafer surface.
So one of the desired features that we wanted for our project was to achieve image stitching, as the size of our image is actually much smaller than the entire wafer. So here on the left, we have a demonstration of that, and on the right is our final prototype actually working. So it exposes steps and it repeats this process until the entire wafer is actually exposed. And so here the video is sped up as the exposure time between steps is about 30 seconds. And here's our final prototype on the left, and the right is a CAD model, including the demagnified image. And so the image is actually a little bit blurry, as you can see up here. And that's because the cameras have a really hard time actually capturing the fine details of the image. And so to actually see how fine our details are, we have to expose our image and then develop it in the clean room. And so here are some of the results, where the top left is our projected pattern, and the bottom left is the actual pattern on the wafer itself that we took with our camera. And these fine lines over here are what's actually being exposed onto the wafer. And on the top right, we have the smallest feature size that we were able to obtain with a pretty good resolution. It's at about 17 microns, meaning that we can actually print circuit components at around this level. However, we do have some limitations. So here is actually our projected pattern again. And we mainly ran into issues with the optical arrangements of our device. So some parts were underexposed, as you can see here, while others were overexposed. And some of the problems that we ran into were the actual arrangements between the EBM and the lenses themselves, as well as modulating the light intensity from the EBM, resulting in under and overexposed images.
So as an overview in general of what we were able to accomplish from our benchmarks, we were able to achieve our cost benchmark. Our total cost of all the components that we used in our final prototype was $1,000. So still significantly cheaper than photolithography methods currently on the market. It is also maskless. We're able to create our patterns without the use of a photomask and get those to expose on a silicon wafer. It is user-friendly. It's not very coding intensive. The user just controls it over a matter of entering a few commands into a terminal and using the standard editor to see the different options. And we are very close to achieving the resolution that I know goal. We wanted it to be around less than 10 micrometers, and we were able to achieve around 20 microns. So this shows that this method of performing maskless photolithography is definitely promising, and with a second iteration with improved optics and resolution, we could definitely achieve the resolution size for doing circuit components. And just in general, further improvements that we would do for another iteration, again, would just be around getting better quality components. Being able to get a higher quality DMZ technology would be able to allow us to achieve an even smaller resolution for our components. Also improving the optical path in general, not only to overcome the limitations of our setup this semester, but also to allow so that the user can manually align as the machine is exposing, rather than just having to only see it after it's developed and under the microscope. So if we incorporated some kind of a beam splitter in our optical path, the user could actually be able to see what's actually going on the wafer surface while it's being projected, instead of having to wait until afterwards. And then finally, incorporating an actual graphical user interface for the user. So instead of having to interact with the actual Raspberry Pi itself, having something else in the front end where the user would just input things like the image they want to do, the exposure time, stuff like that, and have everything else happen on the back end would be something we would definitely want to incorporate in the future iteration of this product. But that concludes our presentation. Our actual physical model is outside on the table. If anyone would like to see it, will be out there for a bit. We just wanted to acknowledge a few people that helped with our process. Our advisor, Professor Lin, Eric Hazen, and Chris Ballard from the EDF for their help with electronics throughout the year. Also the EDF and Professor Hudson for providing us with a workspace throughout the year. And then the BU Clean Room, and then BU Epic and BTech for their additional funding. Thank you, and I'll open up to questions.
Excellent project. Clarify for me, because I know you said at the beginning, there's a step after it gets exposed there that's not shown here. You need to lab for etching, right?
Yes.
Right.
So you wanna-
That's part of the lab itself.
So how we currently introduce circuit is that a photoresist layer is more like a temporary layer where we can create like a pattern, and but the etching itself is the removal of the material underneath it. So what we're doing is that we're making those temporary layers.
There's
Then-
another machine or function elsewhere where you're actually doing that.
Yes.
Okay, that's all.
Those ones are
That's-
more just like chemical based. This is the most expensive part of it.
Right.
Photolithography.
Question. So you talked about your 10 micron resolution. How about your pattern placement tolerance? Of these IC chips, these patterns. Exact location. So how did you manage to do that? And what considerations?
So it's more related to like the actual output of like the lenses themselves. Found that it was about like 2 millimeter by 2 millimeter. So that was like the distance that we had to step. And then from there on, we can actually calculate like the number of steps that we need to expose the entire wafer. So it was more like an optical challenge like that.
And what tolerance were you able to achieve?
Oh, so we were like actually pretty close, but the problem was that we had a lot of like vibrations like in our system, which we like minimized it by actually making the motors like micro step, meaning that it just splits up one step into like 16. That actually helped a lot, but the tolerance itself was about half a million.
What do you think is the biggest limitation to the resolution? Do you think it's optics or is it, are the optical, the projector optical?
I think a bit of both. The actual projector module has a resolution of, I think it was NHD, so it was the cheapest version of the TI ZMD technology, so it was the poorest resolution that was available. So getting a higher quality components would help with the resolution of that. And also, I think our optical setup, we've had a bunch of converging lenses that helps just in general with the focus, but I think an improvement of that as well would help with the resolution just not getting distorted.
So it's like about plastic resolution, some resolution. Resolution you guys are operating at, it's backlash, things been all.
In terms of that, we were never like going back to step and expose pattern, so backlash wasn't really in like consideration of the designing it, because we just have to like let it repeat, like just go on to like a new surface.
What did you consider in the development of those stages? And I'm curious what the base plate,
But the, sorry?
the base plate of the stages were on.
Oh, the wafer, just.
How we met them.
What you considered in the development, linear state.
In turn, like, so we had to, the purpose of the wafer stage was that it would hold the wafer, so it's not like really moving once it's setting. So we have to measure the diameter of the wafer itself, which is 4 inch, and we just have to. Okay. So the diameter itself has like a little thickness that can fit the wafer inside the wafer stage. Then there's a little square spots, so we can use this tweezer to lift the wafer up. But in terms of the thickness doesn't really matter. We just had that because that's the only screws we had, but then it could always be reused. Yeah.
I was more asking about the XY,
Oh, like the motion of the stage itself, or just like.
or the design of the base plate.
So for the motion itself, it was the primary goal is to, of course, be as precise as possible. So I previously mentioned that we set the stepping motion of the motors for the maximum micro stepping. That one reduces like the actual vibration of the output of the motor, as well as just being more precise because you have like basically a wider range of steps per revolution. So that's in terms of the motor.
Very nice presentation. So my question would be, what's the ratio of your loaded pattern versus your actual output? Is that at the range or is it at fixed? Say you're generating 20 micron pattern, what's the original pattern that you loaded on?
So like the total size of like the
Yes.
image, it's like about 2 by 2 millimeters.
And so what's the output?
So we got the smallest one was about or 17 microns, so that's one feature set, sorry, but it just depends on whatever image you actually expose onto it, which is like up to the user, I guess, so. It's like
So is it rather fixed or is it a better?
the overall projected image is fixed because they handle the resolution of the gameplay device. Especially if we use like 640 by 480, but in consideration of that, those 640 by 480 consist of the micro mirrors. So itself is fixed. So if we want a bigger field of exposure, we would have to use bigger resolution gameplay for example, like 990 times 1080 device. Yeah.
Thank you.
What's the advantage of using the
Next
micro
question.
mirror array as opposed to like a galvo setup with a small enough wavelength laser?
So that there's like a technical term, it's called series etching or series process or parallel process. So for this, the advantage is that we can expose surface at the very same time. Then I think what you're mentioning is having the laser to help put on like a point, right?
Essentially.
But that would just take
But the
Right on.
advantage of that would you'd be able to cover the entire wafer with your single laser, you would have to have a can, right?
it would be more precise, but it would take time.
Thank you, group 46.